Hi, this is an introductory video to Bloom filters. What is a Bloom filter? Bloom filters are a space-efficient probabilistic data structure which tests whether an element is a member of a set. A Bloom filter might return false positives, but it can't return false negatives. When you test to see if an element is in a set, the Bloom filter will return either possibly in set or definitely not in set. Why would you use a Bloom filter? Well, you would use a Bloom filter if you wanted to be able to know if a certain element is definitely not in a set, but you don't care what elements definitely are. If you know that an element's not in a set, then you won't have to do any further computation for that element. A Bloom filter allows us to store binary data instead of all the keys or elements, which takes much less space. An example of this is Google Chrome. Whenever you visit a URL, Chrome checks to see if it's in a list of malicious URLs. If it's definitely not in the list, you go to the URL, and if it might be in the list, then Chrome lets you know that you might be visiting a malicious one. But Bloom filters sacrifice exactness for efficiency. Let's run through an example. Step 1 of the algorithm is to initialize an array of n bits. We can also work out that the optimal number of hash functions for these 11 bits is 4. We can then set up some hash functions. For each new element, we apply each hash function. Value generated aligns with the position in the array. For each position generated, we switch the position to 1. It's already 1, we leave it. So let's try with 8. Through the first function, 8 gives us position 3, so we switch position 3 to 1. Through the second function, we get position 1, so we change it to 1. The third function gives us position 7, and the fourth gives us position 4. Let's try for 10 too. 10 gives us 3, 1, 5, so we change that to 1, and 3. All the positions that have not yet been touched are still 0. To see if an element is in the set, we apply the hash functions to find the positions and check to see if all the positions are set to 1. If all positions are set to 1, then the element may be in the set. If any are set to 0, it's definitely not in the set, because if it was, the position would have already been changed to 0. Putting 48 through the hash functions gives us position 3, which is 1, position 1, which is 1, position 7, which is 1, and position 4, which is 1. So 48 is possibly in the set. If we try with 7, that gives us position 0, which is 0, position 1, which is 1, position 4, which is 1, and position 2, which is 0. Some positions associated with 7 are set to 0, so 7 is definitely not in the set. The memory needed to store a Bloom filter scales as the function of the false positive rate at a rate of alpha equals the number of elements over the size of the bit array. The memory needed is the same no matter what the number of elements, as the bit array does not shrink or expand, it is always the size that you made it. We add more hash functions in order to decrease the false positive rate, and the more hash functions we have, the greater the access time. However, having too many hash functions will increase the false positive rate if there's not enough memory to store them. The time taken to access a key does not increase with the number of elements stored. Now let's talk about false positive rates. Well, the theoretical false positive rate is calculated using this equation. The false positive rate for our sample is about 0.07. This is because we have a very small array and our hash functions map numbers to the same slots. So that's a Bloom filter.